Okay, guys, let's start. Okay. Guys, it's impossible that I'll start if you talk. Thanks. Okay. So let's start to talk about the recitation today. So we have 3 subjects. I understood that Izar finished about systems, right? So I won't talk too much about the FIR and IIR because I like to teach them alongside filters because I feel they are highly correlated to each other. So we'll just talk, it's a kind of an introduction. In the next class, we will do about filters. It will be mainly about filters. And in the last one, we will speak about using the spectral analysis for computations, such as correlation, which is computed by coherence, okay, and spectral density. And I am quite sure that Izar won't have time to talk about a phase, which will be probably my subject. I mean, like the phase domain, and probably also not about wavelets. So we have a bit of intensive, it's not that intensive. We have quite a lot to cover. So we have to stay tuned, okay? So I won't talk too much. Oh, by the way, how do you feel now? Are you exhausted? Are you okay, all of you? Did you have a good break? Okay, so we can do it. So just a short reminder that Izar talked about Fourier transform. If some of you feel that they still don't fully understand it, so please watch the last math reinforcement about that. And the main thing that I want you to take now is the idea that when we have a Fourier transform, we can take each signal and discover what are the frequencies that we have in this signal. When frequencies are depicted by sine and cosine function, that each one might have a different phase. For example, here you can see that all of the sines, yes, are with the same phase because all of them are increasing at the beginning of the signal, but they can have different phase. Yet the important thing is how many periods do you have in 1 second. And a Fourier transform is taking a signal that is presented like this, that we have the amplitude and the time, and it represents it in the frequency domain so that our new x-axis is the frequency. Okay, so far so good. Questions? Okay. Okay, so let's see that we fully understand this idea. I didn't check if they hear me. They hear me? No.
Yeah, we do.
Okay, great. Okay. Do you still hear me, Iran? Probably yes. Okay.
Yeah, we do.
Great. So I would like you to tell me what frequencies do you see over here? And here probably it's not fully clear the number, so we'll just start here. Yeah. Yeah, Julio. So we can see for the blue one that we can count the number of periods within each, let's say, 5 seconds. So if we have 5 seconds, let's count the peaks that we have. We have 1, 2, 3, 4, 5, 6, and 7. So we have 7 peaks within 5 seconds, which are these small peaks over here. And we have another smaller wave, you see, that it goes like here. And this one is almost 5 seconds. So we have 2 frequencies. Do all of you see that already in the signal? Great. And now for the red, we can count. We have 1, 2, 3, 4, 5. 6 or more about 5. So we have around 5 peaks within 5 minutes. So this one is 1 hertz, as Julius just said. And also we see over here that we have another wave, which is the slower one. It goes like this, right? So this one is only 1 period, okay? And for the next example, it's not that important, but we can see over here, this is the power spectrum. So the power says what frequencies do we see and what is the size of each one. And we can see for the blue one here, we see the smaller, the wide wave over here, less than 1, closer to 0, because it's 1 within 5 seconds. And also for the red, okay? And here around 1 hertz, we see also another peak for the red and a smaller one for the blue. Okay, so is that clear, the relation between this and this? Okay, so let's see again. So we have, this is a real signal. This is an EEG signal that we see over here. And we want to start by looking at what phases, what frequencies do we see in this signal. So we saw for each one 2 main frequencies that are clear, right? For the blue one, we saw 1, which is very, very slow. It starts here by 0, there is a peak, and there is a slow trough. And by 5 seconds, we have 1 period. So this is around 0.2 or even smaller frequency for the slow frequency of the blue, right? And we have another one, which is a much faster one that we see within each peak over here. And we saw that we have 7 peaks over the 5 hertz, 5 seconds. So 7 over 5 is around 1, right? 7 periods over 5 seconds, it's around 1 per second. So we expect to see 2 main frequencies for this blue one. And we do see them here around 0, it's the slower one. And here around 1, it's the faster one. And in between, we have a lot of other phases, right? Because there are some phases that we don't even notice over here. For example, some of them, this is not like, when I say that this is a full period, there are some smearings of this period. It's not like a clear sign, right? It's not a clear sign function. So for this reason, we have these additional frequencies for the blue. And then we did the same for the red. We counted also the number of peaks and also the slower waves. And this was, the slower was also around 0.1, 0.2. So this is what we see here. And we have these faster frequencies over here, which are around 1, and this is what we see here. Okay, more clear now? So when we are asked what are the frequencies that we see within a real signal, you'll never really see something that is, I'll show the next example, that is like this, that it is really clear that there are this frequency of 15 and another one at 3. It will never be that clear. Also in your project, you will have something that is more similar to real data, and real data is noisy. Therefore, we have some frequencies that are just irrelevant to how the brain works, okay? And these are these small peaks over here that we see over the power spectrum. And we need to, when we start analyzing our data, I feel that you already got it during the course, you start by looking at the real data and looking what frequencies do you see in this data, and then you look at the power spectrum and you see if it is related to what you see with your eyes. Okay? Questions so far? Yes. So the power is always in correlation to the amplitude squared. Is that talked about power spectrum density? No? Not already? Okay, so power spectrum, what we see here, it's a way that we take the frequencies in the frequency domain, and over here, the y-axis could be either the amplitude or the power, which is the amplitude squared. This comes from physics, that you have the kinetic energy, and when you have a transformation for waves, then you see that the transformation for waves is that the energy is the amplitude squared multiplied by something. Okay, so this is what we see here. Millivolt, microvolt square, microvolt. Okay. Why do we have hertz? So this is one of these normalization units that we have here. Okay, so if you remember in the power, I showed that it's the amplitude square multiplied by something which is connected to velocity. And velocity could be defined by the hertz. But the units themselves are not really that important. The main thing is the ratio between the different parts. Okay, so you could, this is like something that you define as a default when you create your spectrum graph, and you just decide about the size of it. Okay? Great. Okay, so just a short reminder of the different formulas that we have when we take from the signal time domain to the frequency. So we commonly use the Euler formula that is given over here. And this formula allows us to take any signal and transform it to bunch of cosines and bunch of sines based on this formula. Okay, and the reason that we really like to use this form here, right? This is the form of the Fourier transform. The reason that we like to use it is that the absolute value of this number will be the amplitude of the wave, and the arctangents between the y and the x will be the phase. Okay, so this helps us to compute the transformation much more faster than using the cosine and the sine version. Okay. Okay. So we have here the two formulas, one for the continuous and one for the discrete. And what I want us to do now is to see how do we use the formula when we want to calculate an example of a Fourier transform. Okay, I want us to really do it analytically. Also, in your project, you will have a question that you will be asked to calculate analytically Fourier transform of a simple wave. Okay, so this is a bit harder, but we'll do it. Okay, so I'll stop the share and I'll close this one for a minute. Okay, so we want to calculate, we have a function, and the function looks like this. This is in the time domain, and we have minus half to half. So this size is 1, okay? And the height of it is also 1. Okay, so this means that we can write the function. Do you see the board? Okay. So we write the function as following: when t is between minus half and half, the function is 1, and it's 0 when t is, we'll just write here else, okay? Is that clear? Great. And now we want to use the Fourier transform. So the Fourier transform is given by the following. Fourier transform in the frequency domain takes the real signal at the time domain and multiplied by minus I omega t and an integral over dt. Okay, so please note that we have here, those three are the variables of our signal, right? And we integrate them to get a new signal that is by this variable, okay? That we see here. So we don't need to assign any number in it, okay? We use only the numbers that are here in the function in relation to the variable of t. So let's see it. So the transformation over omega. So instead of taking from minus infinity to infinity, this might be written as three integrals, right? There is an integral between minus infinity to minus half, and with something here, plus another integral between minus half and half, plus another one between half and infinity, right? Now in each one, we have the function multiplied by something. Over here, the function equals 0. So all of this is 0. And all of this is also 0. So we'll put it here. So we are left only with this integral between minus half and half, right? Yes, because this is, yeah. You can either use the fact that it's a symmetric loop. This function is symmetric. And an integral is a computation of the area under the curve, right? So what Ori is saying that instead of calculating all of this area, we can calculate only the area here from 0 to half, and this would be enough, okay? Would you like to try this option? And then multiply it, of course, by 2. Okay? To assign, yes. Okay, so let's try. So we say that our transform equals to 2 times the integral between 0 and half of the function multiplied by e minus I omega t dt. I'll just close the, I'm sorry about the WhatsApp. Right, so we know that f of t in this region equals to 1, right? So we can write here that this is 2 multiplied by 0 to half e by minus I omega t dt, right? And look at e. Do you know what is the integral of e minus I omega t? Great. So this one equals to minus 1. So we have 2 times minus 1 over omega I of E by minus I omega t between 0 to half, right? And now we need to assign 0 and half over here 2 times. The higher minus the lower. So this one is minus 2 over omega I of E by minus half I omega minus E by 0. And this one equals 1, right? You probably don't see my board. So I'll continue here.
Would it be possible for someone in the class to take a picture of the board because it's a little blurry on Zoom?
Yeah, I'll just also.
Thanks.
Sorry. So, okay. So we are left with x of omega by minus 2 to omega I. The true is that it was not a good idea to do it only between 0 and the half. You will see in a minute. Yeah, it was not a good idea. So sorry. I'll show you now why. So I take off this 2 and I'll keep it between minus half and half. Okay? Yeah. Where? 1 minute, sorry. Where? Okay. So we don't have here the 2, it's always 1. So here it's half, yes. Right. So it's plus half. And now what I want to do is to use the following relation that E by I theta minus E by I theta by minus I theta over 2I equals to sine of theta. Okay? And if we have here, for example, that this one is multiplied by a number, so we'll just multiply it inside by this number. Okay? So look again over here. I'll write it more clearly. So we got that x of omega equals to E by half I theta minus E by minus half I theta. And this is, since I flipped the relationship between them, I'll write here a minus. Okay? So it will be a minus 1 over something. And this one I want it to be divided by 2I. So I can take the I from here, right? So I'll be left only with the omega. And the 2, I need to multiply it by 2. Okay? And when I rewrite it like this, I can use this relation, and this one equals to minus 2 over omega multiplied by sine of omega over 2. And this function has a name. It is called sinc of omega over 2. We can write here with like this. This is equivalent, defined by. Okay? So this is a very important function that we will see again and again during the next recitation. The minus 2 over, wasn't it we had here the minus, so this is a, there is a minus over here. So we need to multiply it by another minus. So it's minus multiplied by a minus, and we don't have the minus anymore. Okay. So this function, this is the harder function for the Fourier transform, one of the hardest to calculate. It's the easiest one when you have a sine or a cosine, and in the project you will have something like this, which is easier, that you see directly what should be the solution. So you can see over here that this function transforms to this one, which is sine divided by what is in the sine. Okay. And again, this is important for us because next week when we talk about filters, we'll talk a lot about why filters are creating this problem of the ripples that are coming from the sinc function. Okay, so please remember this relation. It is very important in relation to real signal data analysis. Yes. We could just, then I couldn't use this relation over here. So this is why I took it back to the minus half. Yes. Right, right, right. Exactly. Yeah, you are right. That so, and you don't calculate only for the rectangle, you calculate for the one which is multiplied. Great. Thank you very much, Austin. Okay, and here I just, I'm sorry for the resolution. I can send it to you from the book. So here are the common relation between between functions, so that the rectifier becomes a sinc and the sinc becomes a rectifier. And an exponent stays the same. Therefore, it is easy to see that the cosine and the sine becomes a delta function, okay? As we've seen. So this is the relation that we will see again and again. Okay, so this is so far. So in the project or in a question that you are asked to calculate the power spectrum, if you do it hand by hand, so I just showed you how to do it, like analytical solution. And if you need to do it by the computer, so you need to see how you do the fast Fourier transform or the discrete Fourier transform, and then you get the power spectrum. So far, so good. Any questions? Are you sure? Okay, so the next thing that I want to talk about, there is a lot of words that are written here, but I want to explain it to you. So I just want to take you back to your first project. It was when you were young, and you believe that this course will be easy for you. Sorry for saying it is easy for you, but maybe you remember that you had a question in project one, the first question that you were asked to plot sine. Do you remember that? And then you needed to sample this sine wave. Do you remember that? And then when you sampled it, one time it was like a really good one like this, right? And in the other one, you had a lower sampling rate, and then your sine interpolated to, you could interpolate it to something like this, I think, right? Remember that you could not really interpolate it in the right way due to the sampling frequency that you had. Okay, so maybe I'll try to explain it in a different way. So today is Wednesday, and every Wednesday we have a recitation, right? And let's say that we have a visitor that comes here every week only at Wednesday. And then he looks and says, okay, every Wednesday there is a recitation in in the building class. Therefore, I conclude that there is a full-time signal and data analysis course all along the year. Right? So the problem is that this visitor came only when he was here, when there was this course here. If he would come even for one more day a week, for example, at Mondays, then he would see that there is a period, right? That there is a class and there are 2 days without class, and there is another class and then 2 days without class. So he cannot tell anything about the cycle or about the data due to the sampling rate that he has, that is too low, okay? So we understand that if he wants to see the cycle of the classes in SDA, he needs to come here at least 2 times a week, right? So since we have once every week, he needs to come 2 times a week. So this is the basic idea of the nyquist frequency. So the nyquist frequency tells us that if we want to know something about the frequency, we need to sample it at least with 2 times this frequency, okay? So in a minute, I'll show you the aliasing, but I'll give you just an example. We have a very good reason to believe in neuroscience that, did you ever hear about the gamma frequency of the brain? Do you know what I'm talking about? So please, would someone like to tell us what is the gamma frequency? To everything, to all of the cortex. Okay. Yeah. Yes. So we know that when neuroscience began, it was very common to use EEG, as you say. And then it was very common to look at specific frequencies, at specific ranges. For example, there is the alpha, which is 1 to 2 hertz, so that you have a cycle within 1 second, or 2 cycles within 1 second. And there was another one of the theta. So this is the alpha, and then we have the theta, which is about 5 to 12 hertz. So we have about every 200 milliseconds, we have a cycle, or even faster. And then there is a famous one, which is called the gamma frequency, which is the highest one. And it is between 30 to 100 hertz. So this means that there is a period within what could be the size of a period? Great. So every 10 milliseconds to 30. Okay? Something like this. And this is considered one of the most studied frequencies of the brain. Since this gamma frequency appears again and again, mainly between around 60 hertz, we see it in a lot of studies. This is related to a lot of cognitive capacities, such as attention, such as working memory, learning. We see that the information flow is much more efficient when there is a gamma frequency. So we believe that gamma frequency is one of the ways that the brain kind of synchronizes the activity across different regions, okay? So this is considered a very, very important topic in neuroscience, okay? So in my lab, we use a technique that the sampling rate equals to 100 hertz. Could we study the gamma frequency at the visual cortex? Right, why not?
We just learned that today.
Right, so the highest possible frequency that I can notice in my research is 50 hertz. Right. This is called the nyquist frequency. This is the top. It should be lower. Yet the problem with gamma that it is around 60. And the more I come closer to the 50 hertz, I have more problems of SNR because I have more noise in my data. I cannot really be sure if this noise is in relation to the fact that I use a camera from the 90s or that my computer is saving in a specific way. I cannot really know what is the reason for this frequency. So I say 50, and in fact, when you have the noise, it's even more around 40 hertz. So I cannot use my method to study the gamma frequency. I can use it to study other frequencies, but this might be a very problematic use. Okay, so this is a real example that we have in our lab, and I hope that it kind of shows you how to use the calculation. So please note that the relation is always that the sampling rate is always 2 times the nyquist frequency. Okay. Now, what happens when we don't use the right frequency? So let's say that I do want to study the 60 hertz gamma frequency in the brain, and I still want to use the 100 hertz. What will happen? Aliasing, great, okay? So what is aliasing? So I want to show you, I found a very, very nice illustration for that. In the book of Dron Gelen that I wanted to send you, this is a great book about signal and data analysis in neuroscience. Can one of you please turn on the air condition? It's the middle switch. Okay, 1 minute. Why does it take so much time? Should have just take a photo of it. Okay, we'll wait just a bit more. Oh, and I'll share the Zoom.
Thank you.
Welcome. Okay, it's still loading for some reason. Great. So figure 2.5. I think it was here. Okay. So you can see here. Uh, 1 minute. I want to have it bigger. Okay. So we have a 20 hertz sine wave that is sampled at different rates. So what is the minimal sampling rate that we need to really have this sine function? The full, yeah. We have 20, so our sampling rates need to be 40, 2 times 20. So here we have an example for a sampling rate of 500 hertz. So you see it over here. And then it was there was a sampling rate of this sine function using a 59 hertz. So you can see what happens when we use a 59 hertz. we can still see the real frequency, but then we had an additional frequency that is composed of it, right? And here we see at 24 hertz, we see that we have a downsampling, so that each one of the dots over here, instead of having this full range, is much more wider, and we don't have the right frequency. So you can see that the lower our sampling rate goes, then we have more and more lower frequencies that are attached to the signal instead of the real frequencies that it has. Okay? So here, although this is almost 3 times, you still have this aliasing. So when we say that the nyquist should be at least 2, this does not mean, so if you want it to be still accurate, this does not mean that you will have the exact sine function. You might still have an aliasing even if you are above the nyquist, okay? Theoretically, yes. But since it is impossible, so we need to be, we need to understand that that we'll always might have an aliasing at some level. Yes. Right. It's not. It's still not the best. So let's say that 3 times it's okay. 4 times it's like a safe zone. Okay, so this is the aliasing, and now I want us to do a nice exercise to fully understand the idea. Okay, this is from an exam. Yeah, I think that will make it today. Are you still on tune? Are you still focused? To some extent. Do you need a few minutes to have a break? Let's finish this exercise and you'll just take, I don't know, 5 minutes even just to stand up and exercise a bit, okay? So we have an electrical frog that has an electrical potential generated by a function of 1 plus x sine of 50t multiplied by 2 pi plus some number cosine 70t multiplied by 2 pi. Okay? So we have a scientist who samples this potential at 120 hertz. What is the power spectrum, or what is the spectrum that we expect him to have? So should there be aliasing? What? Yes, why? Great. So we have here 2 frequencies. One of them is of 50 and the other one is of 70. Irena and Ksenia, I stopped the share of the screen so that you can see the board better.
Okay, thank you.
So we have 70 and 50. So we need at least 140 hertz sampling so that we won't have an aliasing, but we have only 120, so there will be an aliasing, right? So how do we solve this question? So first of all, we need to have a flag of the aliasing. The aliasing is a mirroring effect. It takes the frequencies, it sums them, the real frequencies, it sums them up, and in relation to the sum, there is a mirror, okay? So let's see, in our frequency domain, since we have only between, we have the 120 hertz, so we see only until 60, between minus 60 and 60. Okay, this is our real range. But the reflections will be in relation to another frequency that we will not see. And it is the sum of the frequencies. So what is the sum of the frequencies over here? 50 plus 70. So our mirror, I like to call it a mirror, but because it's more visualized like this. So our mirror will be at 120. Okay? And this mirror is always the 70 plus 50. And also over here, 70 plus 50. Okay. Great. So now let's see. In relation to this 120, we will also always have the aliasing either by subtracting one of the frequencies or adding one of the frequencies, okay? So for our goal, it is irrelevant to look at the subtractions, right? To look at the, not subtraction, at the sums. In the aliasing, you will always have the sum of the frequencies plus minus each frequency, okay? So you sum them up, and then this is your mirror, and in relation to this mirror, you add or you subtract the other frequencies. So if we subtract 50, then we have an aliasing at 70, right? And here also at 70. So this is irrelevant because we don't see it in our power spectrum. Okay, so this is in relation to the frequency of 50. Are you still with me? Right. So the other possibility that we need to subtract the 70. And when we subtract the 70, we have one at 50. So here, it will be at 50, and another one here at minus 50. So the aliasing makes a mirror effect around 120. So this is your mirror. And then you have always like at 70 and at 190, the aliased frequencies. Okay? And also here at 50 and at 170. Okay, I switched, yes. So this is our mirror, and in relation to this mirror, we get the unreal frequencies due to the sampling rate. Okay? So we have here at 50 and at minus 50, and beside that, we do have some real frequencies, right? So we have a frequency at 0. Why? What is the frequency at 0? It's, excuse me? The 1, right. This is called the DC. So this one is the size of 1. And what other frequencies do we see? We can still see the real 50, right? Not only the aliased. So we see also a real one at 50, that its size is, what is the size of this 50? The amplitude is x, great. And here it's also x. And in the aliasing, now we want to know what are the unreal, what are their sizes. So here we subtracted 50, right? So here from 120 to 70, we subtracted 50. So for the 70, sorry, there's something that I don't see here. Yeah, for the 70, it should be here we add x plus y, so it's x plus y minus the 50, so it's minus x, so it should be size of y, right? And here in the unreal, it will be the same. It will be these two sum of the frequencies, so it's x plus y minus y, because here we subtracted 70. Is that clear? So here we have x plus y minus y. This one equals x, and this one is the real x. So together, it will just be the size of 2x. Yes. So yeah, I'm just wondering because in my solution, I see that it is not. For the 120, I see that the size is 1. And here, 1 minute. Here, 170 and the 70, so we add a y. We add a y. Yeah, so this one looks okay. So there is a mistake in my solution. It should be like this. So this one should be 2x. Yes.
You don't take the absolute value.
Yes. Right. And then you make them absolute. Yeah. But here also you can have the negative. No, the aliasing is just the fact that you have this mirror over here, and in relation to this mirror, you say what are the heights. Yes.
The not real frequency is x plus y minus 1, right?
Right.
And the real one is x. How can you solve this?
Because both of them are at the same number. Yes. This is the effect of the aliasing. Okay? So by the end, what we will have here is that our spectrum is just this part from minus 60 to plus 60. And we have here at 0 and at 50, and here it will be 2x.
This is just the real spectrum, right?
This is what you get when you do the Fourier transform, yes, of 2x. Okay, instead of having the real two frequencies. So part of this x is due to the fact that you had this aliasing, and part of it is just the fact that you have the real signal over here. Yes. So the minus 60 to 60 is due to the fact that our sampling rate is 120. So the maximal possible, the maximum of the frequencies we can see is at 60 hertz. It's half of our sampling rate. This is the nyquist frequency. Right. Okay. So another short question, just for fully understanding this idea. Oh, and by the way, there is a nice question here. let's say that this scientist cannot increase the sampling rate, it can only decrease it. So how could he understand if he has an aliasing or not in his sampling?
Is that frequencies is twice the amplitude.
But he doesn't know. He just gets this. He doesn't know. We know that this is the real. Right.
To get the aliasing frequency in other planes.
Great, exactly. So this is like exactly what we do also in reality. So if we are not sure if we have an aliasing, because for example here, you see the 50, this is really nearby the 60. So we can decrease even more the sampling rate, for example, from 120 to 110 or to 100. And then we see if there are new frequencies or if the heights are changing of these frequencies over here. And this means that there is an aliasing. And by so we can compute the size of the aliasing, okay? So if you have here, for example, if you see here, wait a minute. Oh, I said, now I understand what happened. I said over here that the mirror is at the sum. It is not at the sum, it's at the sampling rate. It's at this frequency. So sorry, this is not the size of X and Y. This was the mistake. It is the sum of 1, and it is due to the fact that you have this sampling rate, okay? It will always be 1, and this is the sampling rate. And then it's a mirror in relation to this one. So let's say, for example, now it will be more clear, Araceli. So if we have a frequency of 100, or we'll take 110, so it will be clearer. So if we have a frequency of 110 sampling rate, so this one is at 55, and this is minus 55, right? This is the Nyquist frequency. And our aliasing will be in relation to 110. So it could be either 110 minus 70 or 110 minus 50. How much is it 110 minus 70? 40, right? So this is an unreal frequency over here. And 110 minus 50 is 60, so we still won't see it, but there is a new frequency over here due to the new sampling rate. Is that more clear? The amplitude will be Y, yes. Exactly. Okay, guys, I'll just show you a last example, and I'll keep the systems to the next recitation, okay? So I'll just show the last question because I see that all of you are really non-concentrating. And this makes me think maybe it's not a good idea to do the recitations at 10, just right after Izar. So I think we'll just take it back to the hour of 2, okay? I thought about changing it, but it is impossible for you. So we'll keep it at 2. And just last question. Yes. Yes. 120 is just because this is the sampling rate. So you have a mirror over here that the size of it is 1. This is due to the aliasing effect. It will always be 1 since here, this is 60, so it is double this one. This is the effect. Yes, but still when you draw it only from minus 60 to 60, so it doesn't matter what you have after. Okay? Maybe I'll just sit with you again, okay? Great. Yes.
What like that, because should get 50 because 100 and then something rate is enough to detect 50.
The 50, yeah, you have also the 50. Of course, this is the real. I just plotted here only the unreal. You're right. And then this one is the size of x, and this one is the size of y because we subtracted 70. So it is reflected by the 70 to the amplitude of y, which is the 70 amplitude. Okay. So here, so it is like in the recitation. So here it's y. So it's x plus y. Yeah. And here it is the same. Excuse me? I just really don't hear. 50 is in the range of the nyquist frequency. So 50 is real. We had it in the real data. Do you want us to do it again at 2? Will it be easier for you that we will do again this exercise by 2 and no? Are you sure? Because all of you look so tired and non-concentrating. So I really feel sorry for you. Okay, yeah. In the reinforcement, next time we have only about filters. So yes, we can do more aliasings at the reinforcement. Yes, great idea. Okay, let's have another example, and with this example we finish the recitation today. Okay, we will talk about systems in filters. I prefer it anyhow like this. So don't feel bad with yourself. I didn't want to do systems anyway today. Okay, and I'll also take off the question about systems from your quiz. So don't worry. Great. So we have neuron X, and it fires at mean rate of 2 spikes per second, and its spectrum has a peak only around 9 Hertz. And another neuron Y, which fires at a mean rate of 9 spikes per second, and its spectrum has a peak only around 2 Hertz. Which one of them is possible? The 2 of them, only one of them, or none? So look again. Why? So you need to think what, so the next question is what could be the sampling rate? Okay, so you are right that X is impossible. So let's think about it. So if we had a peak at 9 Hertz, this means that only for X, look, use this side. Okay, so let's look only at X, only at claim X. If we have a peak at 9 Hertz, this means that our sampling frequency is 18. Right, it's double the peak. So we have at least 18 for the sampling rate. So if we have 18, we should have another peak at 2, right? There could not be one only at 9. Is that clear? this has nothing to do with aliasing so far. For the first claim, we just say if we have a peak at 2, if we have a peak at 9, the sampling rate should be at least 18, right? And then it could not be possible that we didn't see the two spikes per second, right? Let's have Y. So for Y, we have a peak at 2 Hertz, but we don't have a peak at 9. So this means that we have possible frequencies between 4 to 17, right? Is that clear why? To have the 9, we need at least 18, right? But we don't have the 18, so it's 4, which is double this one, to 17, okay? So this could be. So we know that the first question is that Y is possible and X is not. This is the right question. Now, what could be the sampling frequency that will alias the frequencies like this? So what we know is that the frequency of 9 was mirrored to 2, right? We don't see the 9, we see the 2. So we could have either at 11 or at 7, right? Why 7? Because if it is 7, so see, if you have here at 7, minus 7 plus 9 equals 2. So you could have a frequency either at 7 or at 11. Yes. So we know that our real frequency should have been at 9. But we have only, I'll just show also the zooms. The real frequency is at 9, but we have only at 2. So this means that we are 7. This means that we could have either 11 minus 9 equals 2. So either a sampling frequency at 11, right? Because this is the mirror of the aliasing. You have at 11, and then you subtract 7 from it. You subtract 9 from it. And then this one equals to 2, right? Or you could be at the other side of minus 7, and when you add 9, you get 2. But here you have a 2 Hertz. Okay? So you could have frequency between 4 and 17. Because if you had 18, then you would have the 9 Hertz peak, but you don't have it.
Sample in 20 Hertz also be no.
There will be no aliasing, yeah. Only of higher frequencies. Okay. Great, guys. So you're off. I'm here for questions. And please talk with Sophie and decide if you prefer to do the recitations right after Izar, or is it too much? I feel like it is a bit too much. Okay. It is easier for all of you, and in a way it's better for me, but I don't want it to be too much hard. Yes.